Hi, welcome to solvinggo.com. This problem has to do with damped oscillations, so say a spring or something with the dampening force, and it's a question about period and quasi-period. Okay, so let me give you the question. We have a vibrating system satisfying a particular differential equation. Okay, so the differential equation is, let's see, vibrating system satisfying u double prime plus gamma mu plus mu prime plus u, not mu, u equals 0. Okay, so here gamma, let me see if I can draw a better gamma. Gamma is the dampening constant. Okay, so we assume the dampening force is proportional to u prime, so we have this term in here, gamma times u prime. So we want to find gamma such that the quasi-period of the damped system above equals the period of, so it's actually it's 150%. So is is 50% greater than the period of the undamped system. Okay, so that would mean the undamped system would be when gamma is 0. So undamped system is u double prime plus u is 0. Okay, that's the damp and that's the undamped. So let me remind you what the quasi period is. So remember, the period is the period of an oscillating system is the time it takes for a periodic function to go through one cycle. So a damped system, we don't have quite periodic behavior, but something sort of close. Okay, so maybe, just as an example, a damped system might look like this. Okay, eventually getting smaller and smaller. The quasi-period would, say, be the time from here to here. Okay, that would be one example. Okay, so a second would be here to here. Okay, quasi-period, and so on. Okay, so let's see. We want the quasi-period of the vibrating system here. The dampened period, or the quasi-period, is 2 pi over mu. Okay, and mu is given as 4km minus gamma squared to the power of 1/2 divided by 2. Okay, and here, well, for us, we have, so the more general system is the following. So m double prime plus gamma mu prime plus k mu is 0. Okay, so for us, m and k are both 1. So our mu, rather, so this is a Greek letter mu, is, so let me erase this. We have k and m are both 1. And so mu here is 4 minus gamma squared to the power of 1/2 divided by 2, which means our quasi-period is 2 pi divided by this, which is 4 pi divided by 4 minus gamma squared to the power of 1/2. Okay, that's the quasi-period. All right, so let me keep this down here. So this is the quasi-period period of the damped system. And now for the undamped system, we want to get its period. It is u double prime plus u is 0. The characteristic equation is r squared plus 1 is 0. So the roots are r equals plus or minus I. And so the solutions are u equals c1 cos t plus c2 sine t. Okay? And the period then is 2 pi. So it's usually 2 pi over this constant, the angular frequency, or the angular. So it's what's written as omega 0. But for us, we can see we just have sine and cosine. So we know sine and cosine are 2 pi periodic as functions. Okay, so the period of, so this is t. Okay, so we have period of the undamped, so I'll write that as tu, period of the undamped was 2 pi. And then we want the period of the damped system, which is 4 pi over 4 minus gamma squared to the power of 1/2, to be equal to, it will be 50% greater than this. So we can multiply by 1.5. Okay, 50% greater than 2 pi. And 1.5 is 3 over 2. So we get some canceling happen. We get 3 pi on the right-hand side here. Okay, so then simplifying this, some pi's cancel. We get 1 over 4 minus gamma squared to the 1/2 is 3 over 4. Okay, so flipping some fractions here. 4 minus gamma squared to the 1/2. Let me see. Is 4 over 3. 4 minus gamma squared is then 16 over 9. And then we get 4 minus 16 over 9 is gamma squared. And so gamma squared then is 36 minus 16 is 20 over 9. And then finally we get gamma. So gamma is the square root of 20 over 9. And that's the solution to this problem about period and quasi-period of a damped or undamped system, as the case may be.